Okay, here we go. This is section 10.6 on alternating series, and it is the last of the setup for the power series and Taylor series that are the real value of chapter 10. I find this to be one of the easier ones, at least the most intuitive of all the ones we've done. It's mostly just a few definitions and kind of graphics to show what this stuff is all about. And I hope you find it to be pretty straightforward too. So it won't be a very long lecture, which I'm sure you'll be happy to know. So far, all the tests we've done so far have required, so all the tests, all tests so far required positive terms. Require that a sub n is greater than 0. So today is the first time that we're going to really look at alternating series. And we will make some definitions for absolute and conditional convergence. Okay, so we'll get right into it, and I'll throw the first definition in there, and that is something called the Leibniz test. Leibniz test. And so what does this say? It says the series, which is the sum from n equals 1 to infinity, of here's this negative 1 to the n plus 1, negative 1 to the n plus 1, so it starts at 2, which makes it positive, of u sub n equals u sub 1 minus u sub 2 plus u sub 3 minus u sub 4 plus dot 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 dot. Converges if all three of the following conditions are satisfied. And these are all three very important. 1, the u sub n's are all positive. Now what that means is that the u sub n is really the absolute value of sub a sub n. All right, u sub n just means it's positive. And there's something else, in this case it's negative 1, that causes the sign to change. 2, the positive u sub n's are eventually non-increasing, i.e. U sub n is greater than u sub n plus 1. Now, to me, it makes more sense to say it like this. U sub n plus 1, because that's really the next one, is less than the one that came from before. And that means non-increasing for all n greater than some big N. That means at some point it starts decreasing. The tail, I'm going to write this down, the tail is, I like to say decreasing, even though that's not mathematically great. The tail is decreasing. And thirdly, u sub n's go to 0, right? And this is that nth term test again. This is kind of an extension of the nth term test. These things have got to go to 0, so we're not adding anything by the time we get to the end. Now, where does this alternating thing come from? The sign flip-flop. These are a few of the features, but not all the features that could cause that. First of all, we've got negative 1 to the n. Right, we've seen that one. Oftentimes we'll see it, depending on where we start the sequence, it could be negative 1 to the n. It might be plus or minus 1. You know, so we start at a positive or we start at a negative. We can kind of have a little control over that. Another one that we might see is cosine of n pi, right? Because at 0, the cosine is 1, and at pi, it's negative 1. At all the odd multiples of pi, it's negative. Or we could do one of these, sine of n pi over 2, right? At the even multiples of pi over 2, it's positive 1 up at the top of the unit circle. At the odd multiples of pi over 2, it's negative 1 down at the bottom of the unit circle. All right. So this it says it converges here, and I think there's a really cool graphic that kind of shows this really well. I'm going to stick that in here. 10.6, we're looking for this alternating graphic. So why does this guarantee to converge? Let's take a look at this thing here. I think this is really cool. That's as high as I can get it. So let's say we start at 0 down here, and we add the first term, which is positive, which gets us up to here. Now we know it's alternating, so the next one is going to be negative, so we're going to go back to the left. But, very important over here, it's not increasing. So the next term is a little less. It's negative and less than the first one, so it goes back this way. Not all the way back here. It can't go back here because the magnitude is smaller. But it goes back this way some distance. All right, now we know the next one is positive. The next one moves over this way, but not as far as this one. So we're already trapped. You know, the sum, these are all partial sums down here, S sub 1, S sub 2, S sub 3, S sub 4. The next partial sum is always trapped between the previous two partial sums. So therefore, the limit has to be in here somewhere. You know, all our other tests regarding convergence are now irrelevant if we have this alternating series. But it's very, very important. Must meet all three for this little graphic to work. And these all three are, that doesn't work very well, but must meet all three of those. I'll draw another arrow there. Okay. So that's important. But I think this is pretty cool that you know, we spent all this time working on does it converge, does it converge, does it converge. If it alternates, it converges. And we'll talk about that more in a little bit. But I'm going to stick in another little theorem here, and that is the alternate series estimate. And this is kind of a powerful one too, very useful for us later on. If the alternating series blah 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 satisfies all three conditions of theorem 14, that's over here, Leibniz's test. I like to call it Leibniz's test because, well, he's German, and I favor all things German. Then for n greater than some big N, the partial sum will be u sub 1 minus u sub 2 plus u sub 3, blah, 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 plus this. It'll approximate the sum L of a series. Okay, so it approximates this L. And the absolute value of the error, so how far am I from the actual L, will be less than the next one. Right, well, if I go, so that means if I stop at partial sum 4, then the absolute value is less than this next increment here. So if my S sub 5, which is, you know, I have to add an A sub 5 to get up here, or U sub 5, I guess, in this notation, I know I'm going to cross the limit again. I have to cross the limit. So that means my error, once I get to S sub 4, my error is less than U sub 5. That's pretty nice. Furthermore, the sum L lies between any two successive partial sums. So if I have S sub 2 and S sub 3, say that I'm lazy and that's all I wanted to calculate, S sub 2 and S sub 3, I know that my L lies between those two. Or if I get as far as 4 and I want to go to S sub 5, which I know would be here, so this would be S sub 5, I know that the limit will be between S sub 4 and S sub 5. And you know, that it seems like for all the work we've done, 10.1 through 10.5, now these alternating series really make things pretty easy. So let's take a look at an example of that. Where is my pointer? Down here. So an example would be the sum as n goes from 0 to infinity. Now this the 0 here, 0 will become more common And that's primarily so that we can get our first term always to go to 1. So keep an eye out for that, especially the next couple sections. And let's make this one -1 to the n over, or times 1 over times 2 to the n. And what will that equal? That will equal, I'm going to write it down here so I have a little more room. The first term will be 1, because -1 to the 0 is still 1. 1 over 1 is 1. Minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus 1/32 plus ... Now I came up with a few sums. We know this is 0, 1, 2, 3, 4. The 16th one is actually 4. And the 1/8 is the third. So S sub 3, and I did this in a little Excel spreadsheet, and I'll show you guys how to do that, comes out to be 0.6875. That's the partial sum. 1/8 is not equal to this. That's the sum at this point. The next sum, S sub 4, equals 0.65625. Okay, now according to our alternate series estimate, the next one should fall somewhere between these two, right? The next partial sum should be between there. Sure enough, S sub 5 equals 0.66406. And that's after that sum there. Again, let me reiterate that 1/32 is not 0.66, right? This is almost 2/3, and this is very small. This is the partial sum once we've included the -1/32. And so I'd like to point out that there's another video with the Excel demo. For this one. And if you have not used Excel, if you struggled with that one previous problem, you may want to watch that. Okay, so now let's look at a couple more definitions. I'll squeeze them in over here. It makes a little more sense to put them here. And the first one will be the definition of absolute convergence. So here it is, absolute convergence. There we go. And what does this one say? A series A sub n, sum of A sub n, converges absolutely, or we can say absolutely convergent, if the corresponding series of absolute values, sigma A sub n, absolute value of A sub n, converges. What does this mean? This means, and I'll put this in English, this does not need alternating signs in order to converge. So, for instance, if we look back over to this one on the left, we know that even if we made these all positive, this is a geometric series. Common ratio is 1/2, right? Even if I took the absolute value of all these things. And this would still converge. In fact, this one converges on 1 over, well, let me just write this down. The sum of, from n equals 1, actually, no, that's a 0 to infinity of the absolute value of this thing, -1 to the n times 1 over 2 to the n. So even if I ditch the negative signs, this still converges on 1 over 1 minus 1 half equals 2. So that still converges even without the negative signs. Now that might lead you to guess that the next one is the conditional convergence. And that goes here. And so this one does need the negative signs. That one does need the negative signs. Well, what's a good example of that one? Let's take a look at this sum. And you'll see why I'm going to go from 1 to infinity of -1. Right? This is one of my tricks I use to get things to alternate, to the n minus 1 of 1 over n. So what is this? This is the harmonic series, right? Except we've added this little element here to make it alternating. So this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus dot dot dot. Right. Now this one does converge. Let's do a quick Leibniz check of this one. Quick Leibniz test. Right. What did the 3 conditions of the Leibniz test say? One is that all u sub n greater than 0. 1, 1/2, 1/3, 1/4, 1/5. Yeah, that works. All right, so they're all greater than 0. Let's do some green. Gratuitous use of color. I told you guys it's coming. What's the second of the Leibniz test? Anybody remember? 2. All u sub n plus 1 is less than the term preceding it, u sub n. So it's decreasing, or as the book likes to say, non-increasing. But I think decreasing makes more sense to a simple engineering mind like mine. And since you're all headed for engineering mostly, that's good. And 3 is that u sub n goes to 0. Right? And we know that 1 over 5, 1 over 6, 1 over 7, they're definitely going to go to 0, so we can check that off as a check. So it passes Leibniz test, therefore it converges. Right? Even though it's the lowly harmonic series. It could be 1 over the square root of n, and it would still converge. Right? So finally, and it seems remarkably fast that we're almost done with this one. Let's go to the next page here. I'd just like to sum up in black that it seems like a waste of a page to put this in here, but I'm going to do it anyway. Absolute convergence right? So to do this, it must, and I'm going to write in quotes here, pass one of the tests from 10.2 to 10.5, right? Because we lose the negative sign. We don't have the negative sign anymore if we're checking for absolute convergence. However, for conditional convergence, Well, that only needs to meet 3 parts of Leibniz's test. So that's it. Section 10.6 in 15 minutes or less. And remember, if you're interested in the Excel, watch that Excel video that's coming up next.